This is part 1 of tutorial 2, goal programming. Here's our first example. A small aerospace company is considering 8 projects. These are the projects. And each project has been rated on 5 attributes: return on investment, cost, productivity improvement, worker requirements, and degree of technological risks. And the company has set the following 5 goals. Goal 1, achieve a return on investment of at least 3,250, limit cost to 1,300, achieve a productivity improvement of at least 6, limit manpower use to 108, and limit technological risk to a total of 4. Now here it's explicitly stated that these are goals. These are going to be formulated as soft constraints. But how do we know that we have a goal programming problem if it's not explicitly stated like this example? Well, we can try to formulate the problem as a linear program and formulate these goals as hard constraints, as we usually do, and see what happens. Okay, so first of all, we define our decision variables. Xi is binary, equal to 1 if the project is selected and 0 otherwise. This is very similar to the last problem we did last tutorial. Okay, we define our parameters, and we can here are the goals formulated as hard constraints. So the ROE constraint is going to be formulated like this. You can see the signs here. Okay, let's try to solve this problem using these linear constraints, hard constraints, and see what happens. As you can see, there is no feasible solution found. This is because there is a conflict between the constraints. We can't satisfy all these constraints at the same time. We're going to have to find a good compromise between these constraints. So we don't have to satisfy all of them completely, but we have to find the best compromise. Okay, so to turn these hard constraints into goals or soft constraints, we're going to have to define deviation variables, EJ and UJ. EJ is going to be representing the amount by which the left-hand side exceeds its right-hand side value in goal J. This means that it is the amount by which we're going to exceed that goal, while UJ is the amount by which the left-hand side falls short or under its right-hand side. This means that it is the shortage. It is the amount by which we are short of our goal. Okay, so we're gonna take the exact same constraints we already saw in here, and we're just going to add to each goal, to each constraint, we're going to add plus U1 and subtract E1. So we add the shortage and we subtract the excess, and replace the greater or equal or smaller or equal signs by an equal sign. We do this for all constraints, and we end up with this model. Okay, now for the objective function. What are we supposed to minimize or maximize? Well, for goal programming, we always have to minimize. We never want to maximize our deviation variables. We always want to stay as close to our goal as possible. For example, for goal 1, we do not want to fall very short of our goal of $3,250 in return on investment. So we minimize the shortage amount. We minimize U1. It's okay if we exceed this amount, of course, because it's a return on investment. It's something we want to happen. But it could as well be 0. We don't know yet. We do the same thing for the rest of the goals. For the cost, we want to reduce the excess. We don't want any extra costs. So we want to minimize this value. For the productivity, it's the same as the ROE. We want to maximize. We want excess productivity, or the exact same productivity as stated in our goal, but we don't want to fall short of this goal, so we minimize the shortest, U3. For the manpower, we minimize the excess as well, because we don't want to hire extra people, so we minimize E4. For the risk, we want to have as less risk as possible, so we're gonna minimize the excess risk. So we're going to end up with this objective function, minimize Z equal to U1 plus E2 plus U3 plus U4 plus U5. Okay, so in addition to our goals, of course, we have to state that xi is a binary variable and the deviation variables are greater than or equal to 0. So I went ahead and tried to implement this problem in Lingo and Excel. We're just gonna see what the best compromise is. Okay, solve the problem. We can see we no longer have a non-feasible solution. We actually have a solution here. So we can see that project 1 and project 7 are selected. We're gonna move to the Excel interface to see how well our goals were satisfied. So our goal for the ROE is supposed to be 3,250, but we have achieved 3,570. This gives us an excess of 320, so that's good. We want more ROE. For the cost, we can see that we have $100 excess, which is, not very good, but not that bad as well. This is the minimum amount we can have of excess. We have completely satisfied the productivity goal. We have 6. For the manpower, we actually fall short of our goal, which is good. We want to have less manpower allocated to the projects. For the risk, we actually exceeded the goal by 1, which is, not perfect, but it's a good compromise. Okay, we're gonna go back to the Lingo output and look at the objective value. What do you think this objective value means? Well, nothing actually. We can't really interpret it. It's a sum of deviation variables. So it's useless to try to interpret it. Okay, now we're going back to the example, and we're gonna read the last sentence of our exercise. All the goals are assumed to have roughly the same priority level. This means that our objective function will not have any weights, as you can see right here, and this means that the problem is a non-preemptive goal programming problem. None of these goals dominates the others by a significant amount. Okay, this is it. This is the non-preemptive goal programming example. I hope it was clear. Let me know if something is ambiguous. Thank you for your attention.